All right, let's dive into a massive cosmic mystery, one that suggests our entire understanding of the universe might be fundamentally wrong, and yet somehow incredibly right at the very same time. Our whole story really boils down to this one famous idea from the statistician George Box: all models are wrong, but some are useful. It's this brilliant way of saying, look, our scientific models are always just simplifications of a super complex reality, but that doesn't stop them from being unbelievably powerful tools. And that's the big puzzle, isn't it? If our models of the cosmos are just approximations, if they're technically wrong, then how in the world have they been so ridiculously, so unreasonably good at predicting how everything works? To really get that, we first need to appreciate just how shockingly powerful these wrong models can be. And this brings us to this amazing concept known as an unreasonable effectiveness. So, back in 1960, a physicist named Eugene Wigner wrote this legendary paper about this very thing. He was just blown away by how often pure, abstract mathematics, ideas that were sometimes cooked up with zero thought for the real world, turned out to be the perfect language to describe physical reality. I mean, just look at his examples. Think about Newton's law of gravity. It starts with a simple falling apple, but then it perfectly describes the orbits of entire planets. It's wild. Or quantum mechanics. This totally abstract matrix math just happened to perfectly predict the structure of the hydrogen atom. And then there's quantum electrodynamics, a purely mathematical theory that matched experiments to better than 1 part in 1,000. It's like we got way more out of the math than we ever put in. But here's the thing. Even the most powerful models eventually hit a wall. They have a breaking point. And when they break, it's not a disaster. It's a huge opportunity. So let's look at this famous historical example, a so-called catastrophe. So let's rewind to the late 1800s. Physics was facing this massive crisis that got this really dramatic name, the ultraviolet catastrophe. The problem was pretty simple, actually. Classical physics, the model that had worked perfectly for ages, made a prediction about the light from a hot object that was completely, totally absurd. So here's the problem in a nutshell. On the left, you see what the old theory predicted. It said that at shorter wavelengths, like ultraviolet light, the energy blasted out should just go up and up and up to infinity, an infinite amount of energy, which is, impossible. But reality, on the right, showed something completely different. The energy hit a peak and then just dropped off. The model wasn't just a little off, it was fundamentally broken. So what was the fix? It was this totally radical new idea from Max Planck. He said, what if energy isn't a smooth, continuous flow? What if it comes in these tiny, discrete packets, or quanta? And boom, that one tweak fixed the model perfectly. So the crucial point here is that this catastrophe, this failure, wasn't the end of the story. It was the birth of a whole new revolution in science, quantum physics. And that brings us right up to today, because right now, cosmology is facing its very own ultraviolet catastrophe. It's a conflict that we're calling today's cosmic tension. See, our current best model of the universe, our cosmic map you could call it, is something called the lambda CDM model. It has been wildly successful. I mean, it explains almost everything from the Big Bang to how galaxies form. But right now, that model is straining at the seams. And it's all because of a fight over one single number, the Hubble constant, which is just a measure of how fast the universe is expanding today. Okay, so this chart lays the whole problem bare. On one side, you've got the expansion rate our model predicts based on light from the early universe. This comes from the Planck satellite, and it gives us a value of about 67. But then, on the other side, we have direct measurements of how fast things are expanding in the late universe, stuff closer to us, and that gives a value of about 73. Both of these measurements are super precise, and they just don't agree. They should match, but they don't. And we're not talking about a small rounding error here. In statistics, this is what's known as a greater than 4 sigma tension. So what does that mean? It means the chance of this just being a random fluke is ridiculously low, like less than 1 in 10,000. It's almost certain that this isn't just a measurement error. Something deeper is going on. So if it's not a mistake, what is it? Well, this is where it gets really exciting. A lot of cosmologists think this tension is our first real concrete clue that there's new physics out there, something beyond our standard model. This has forced scientists to ask a pretty revolutionary question. What if the Hubble constant isn't actually, constant? What if the universe's expansion rate is changing in a way that our current model just doesn't know about? And check this out. We're actually starting to see hints in the data that this might be true. When scientists plot the value they measure for the Hubble constant based on how far away they're looking, they see this descending trend. The value seems to get smaller the further back in time we look. And this really shows the whole pattern. The values for h0 that we measure nearby are always higher, lining up with that 73 number we saw. But the values from farther away are consistently lower, trending down towards that 67 number from the early universe. So this isn't just two numbers disagreeing. It might be a whole continuous process that our model is completely blind to. Okay, so what does this all mean? Where does this leave us? Well, it's time to tie all this together with a really powerful analogy: the map versus the territory. A philosopher named Alfred Korzybski famously said, "The map is not the territory." The idea is simple, right? A map of a city can be incredibly useful for getting around, but it's not the city itself. It leaves things out, it simplifies things. In a very real sense, the map is wrong. And that's exactly what our cosmological model is. The Lambda CDM model is the best, most detailed map of the cosmos we have ever created. But the Hubble tension, that's a giant signpost screaming at us that we've reached a spot where our map no longer matches the territory of reality. But here is the most important takeaway of all. This wrongness is not a failure, not at all. Just like that ultraviolet catastrophe, it's the most exciting thing that can possibly happen in science. This is our signal. This is the universe basically telling us, hey, you're about to discover something brand new and amazing. So, the Hubble tension has shown us a crack in our beautiful map of the universe. The real question, the one for the next generation of scientists to answer, is this: what incredible new territory, what new physics will we find when we draw the next map to fill in that gap?